Right. This is Siafunda one more time. I want us to look at grade 11 cycle geometry. It is important that when you go to your tests or your exams in cycle geometry, this becomes your key. This becomes your memo. Once you understand your theorems, because it is them that you'll be applying. Let's recap once more. The angle at the center, a line drawn from the center of a cycle to the midpoint of a chord is perpendicular to a chord. We should always know that whenever we've got this scenario, this angle there will be 90 degrees. What is happening in the second one? A line drawn from the center of a circle perpendicular to a chord, it will bisect the chord. We should always know that if we've got 90 degrees here and this radius this line is coming from the center of a circle, then these two sides will be equal. Whenever we've got an arc that subtends the angle at the center, the same arc subtends the other angle at the circumference. The angle at the center will be 2 times bigger than the one at the circumference. This is the same diagram, but this is the same theorem, but different diagram. This one subtends it at the center, this one subtends it at the circumference. So the angle at the center will be 2 times bigger than the one at the circumference. The angle at the center is 2 times bigger than the angle at the circumference. So since this is 180, that will be 90 degrees. This is the diameter. It subtends that angle there. So we say this is the angle subtended by the diameter. It will always give us 90 degrees. Or others, they will say semicircle, and angles in the semicircle. This next one, this arc subtends this angle at the circumference. The same arc can also take us to that angle at the circumference. Therefore, those two angles are the same. Remember when we did the proof of this theorem, we had to create the center. There's a center, there's a center, there's a center. So when the statements talk about the center, you think about these 3 theorems. When the statement talks about the tangent, you think about these 3 theorems. When the statement that you are reading talk about the cyclic chords, you think about these 2 theorems. What are these saying? The angle between a tangent and a chord, you go to your chord, you go to the circumference. Then that angle that is between the tangent and the chord, it will be equal to that angle. If I'm coming from this side, this angle which is between the tangent and the chord, I go with my chord to the circumference. So that angle will be equal to this one. We call that the tan-chord theorem. Coming to this one, whenever I've got a radius, if it meets the tangent, it will always be 90 degrees. It doesn't matter where it comes from. It can come from that position. When it meets there, this will always be 90 degrees. Coming to this one, theorem number 8, it says that whenever we've got 2 tangents that are coming from the same point, they'll be equal up to the point of contact with the circle. It means that that side will be equal to this side. 2 tangents from the same point, tan radius, tan-chord theorem, center theorem, same segment. Yes, not same segment, subtended by the diameter and same segment. Let's come to the cyclic quadrilaterals. There are only 2. Remember, if I've got, I think it's important, this angle plus this angle is 180 degrees. When I prove this, I've got to take my construction from this other 2. If I'm proving that this is equal to this one, so this angle plus that angle, it is 180 degrees. Whenever we've got opposite angles of a cyclic chord, when we add them together, it is equal to 180 degrees. So in other words, whenever we've got something like this, if we've got maybe, give it to me, if this is 90, for example, let me just say 90, or 110. 110 plus what will give us 180 plus 70, if this is 70. This is 110 degrees, this is 70. When I add these 2 angles, what do we get? I get 180. Remember, if this plus that is always equal to 180, means that it is a cyclic chord. In other words, if this angle plus this angle, it is 180. Therefore, it means that we can draw a circle around that quadrilateral. So this will be concyclic. Same thing applies to this one. If I've got something like this, a figure like this one, if this angle here is equal to that angle, therefore this will be concyclic. In other words, I can draw a circle around here. Around here. So that becomes important. So what is the theorem saying? The exterior angle of a cyclic chord is equal to the interior opposite angle. So whatever when we read those statements, we think of these theorems. Nothing else but the theorems. Now, how do we apply these theorems in real life, in these problems? Let's read. In the figure below, RDS is a tangent. RDS is a tangent. There is an important word there that's clicking, tangent, tangent. So when we say tangent, which theorems must we think of? Which theorems has to deal with a tangent here? It's these three. Tangent, tangent. It directs me exactly to where to find the solution. Let's read again. In the figure below, RDS is a tangent. It is a tangent. So it directs me to these theorems. Can I see these theorems in this diagram? Before I even look at questions, let's check those theorems in this diagram. Let's look at theorem number 6. It is a tan chord theorem. This is a tangent. What is this line chord? It is a chord. So if I've got a tangent and I've got a chord, I've got to go to the circumference for these two to be equal. It's the same scenario here. This is a tangent. This is a chord. Where do I go with my chord? To the circumference. It means that this angle will be equal to this one. Right. So that's what we pick up from that information. There are so many other things. What is this line called from there to here? What is this line called from there to here? What is this line called from here to here? It is the radius. What happens whenever a radius meets a tangent? So it means that this whole angle will be 90 degrees. Right. So those are the things that we look for when we read our statement first. In the figure below, RDS is a tangent to a circle O at D, right? If BC is equal to DC, BC is equal to DC, what is this saying to us? Now, once we have such a scenario, it will mean that this triangle here, do you see this triangle here? This particular triangle. Your grade 8, grade 9 comes in hand here. What type of a triangle is this one? This is an isosceles triangle because these two sides are equal. If these two sides are equal, then the angles will be equal. This side is 9 angle that is opposite it. This side, 90 angle that is opposite it. So it means that these two angles will also be equal. It's important to note that we're getting it from the fact that BC is equals to DC. It makes this an isosceles triangle. An isosceles triangle has got two properties. One has to deal with sides, and the other one has to deal with angles. So this side is equal to this side. So this angle is this side. The angle opposite it is this one. And this side, the angle opposite is that one. So these angles will be equal because they will be equal to angle opposite to those sides. Or others will simply call it the base angles of an isosceles. We are also told that CDS is 40 degrees. This angle here is 40 degrees given. Calculate number 1. We've got to find the size of angle BDC. Let's look for that in the diagram. BDC. BDC. We're looking for this angle. Angle D2, in other words. BDC is angle 2. But what do we know about this angle? It is equal to that angle. So if you can find that angle, we'll definitely know this one. So let's try and look at the theorem that we'll be using to find that. What is it that we know? We already know that this angle, it is 40 degrees. And where is this angle? What is this? It's a tangent. What is this? It's a chord. Do I have any theorem that deals with a tangent and a chord? Yes, we do have it. This one. The angle between a tangent and a chord is equal to the angle in the alternate segment. In other words, angle D1 is equal to 40 degrees. We are given that. In other words, D1 is equal to 40 degrees. That we are given. Also, angle D1 is also equal to angle B. Angle D1 is also equal to angle B. Yes, just angle B1. Why are those two equal? It is because of the theorem, tan chord theorem. Tan chord theorem. Because the angle between the tangent and the chord is equal to the angle and the alternate segment. So in other words, B1 is also equal to 40 because they are equal. But B1 is equals to angle D2. Let's call it the way that they've called it there, angle BDC, which is D2. If these two are the same, and this one is 40 degrees, so it calls for this one also to be 40 degrees. Therefore, angle BDC is equals to 40 degrees. Right, because it is equals to angle B1. This is where we started. We said this one is equal to that one, tan chord theorem. This one is equal to this one, isosceles triangle. If this is 40, therefore this will be 40 degrees. Right, that's how we go about solving 7.2.1. Let's look at the next one, angle C. Where is angle C? Ah, okay. We can see where angle C is. Remember, this is a triangle, an isosceles triangle. What is the sum of angles of a triangle? This was 7.2.1. Let's do here 7.2.2. What is the sum of angles of a triangle? Whenever you've got any kind of triangle, the sum of the interior angles will be 180 degrees, meaning that this angle plus that angle is 180. Remember, this 2 will give us what? This 2 gives us 80. So what is that one? It is 100 degrees. So it means that whenever I add this angle plus that angle plus that angle, I must get 180 degrees. So in other words, angle C plus angle B1 plus angle D2 must be equal to 180 degrees. The reason, the sum of interior angles of a triangle. I'm looking for C. It will be equals to, what is D1? D1 is 40. C plus 40 is equal to 180 degrees. Let's take this 240 to that side. It will be minus. Therefore, angle C will be equals to 100 degrees. So we know the value of this one. It is 100 degrees. It is 100. Right. We do have angle C now. It is 100 degrees. What is the next one? The next one that we are asking for here is 7.2.3, this one. We're looking for angle A. Angle A, let's find it here, 7.2.3. Let's look for angle A. Where is angle A in my diagram? Oh, I can see it. There is A. There is angle A. Okay. How do you go about solving for angle A? Let me check. I think of my theorems. Okay. I can see this. This is where A is. Look at this feet. Look at this one. Look at this one. Look at this one. What do you call this diagram there? What do you call it? What do you call this? Right. This is what we call a cyclic quad. It is these two theorems. This one or this one. What do you know about these theorems? This angle plus this angle is 180. This angle plus this angle is 180. This one is equal to that one. Let's see which one will apply here. When I look at this, we don't have an exterior angle. There's nothing that is being extended. There's no exterior angle. So we can't use that one. We can't use the exterior angle there. So we go to the first one. In other words, we know that this angle plus this angle is 180. This one plus this one is 180. What are we looking for? We're looking for angle A. But we know that angle A plus this angle, angle C, must be equal to 180 degrees. Reason, opposite angles of a cyclic quad. Right. Whenever I've got opposite angles of a cyclic quad, they will always give us 180 degrees. Angle B plus D is 180. That one plus that one is always equals to 180 degrees. So that becomes our memo whenever we're dealing with cyclic geometry. We're looking for A, so C has got to go that side. So angle A will be equals to 180 minus C. What was the value of C in this particular case? It is 100 degrees. Therefore, A will be equals to 180 minus 100. It is 80 degrees. So this is the value of angle A. The alternative way of finding A, let's check it. If we do have another way of finding A, the theorems and A, theorems and A. This is a tangent. Do I have a chord that goes to A? Yes, I do. This chord does not go to A. I can't go to A with this one. Can I go to A with this one? Yes, I can go to A. Right, this is the chord. This is the chord, this is the tangent. What is the value of the angle between the tangent and the chord? Look at this angle here. If this is the chord that I'm going to use, look at this angle. Where is this angle? It is between a tangent and a chord. The angle between a tangent and a chord is equal to the angle in the alternate segment. What is the value of this angle? 40 plus 40. This whole angle is 80 degrees. So what should A be? The angle between a tangent and a chord is equal to the angle on the alternate segment. The angle between a tangent and a chord is equal to the angle in the alternate segment. So when you say that this angle, because it is between a tangent and the chord, it should be equal to the angle in the alternate segment. So if this is 80, that one must be 82. That's another way of finding the same 80 using another theorem, the tan chord theorem. Right, that's how we find A. The next one that we need to find is O1. Remember that we already have the value of A now, which is 80 degrees. We have this value, which is 80 degrees. Now we're looking for O1. O1. When you look at angle O1, where is angle O1? Where is angle O1? Ah, it is at the center. When angle O1 is at the center, what center? Which theorems do I think of? I think of theorems that has to do with the center. Which are those theorems? These are the theorems that has to do with the center. There are just 1, 2, 3. There are 3 theorems. We can see this theorem in this diagram. This one subtends angle O1, the one that we are looking for. That one subtends that one at the circumference. Which one is big? The one at the center is 2 times bigger than angle A. What is the value of angle A? It is 80 degrees. What then will be the value of O1? If this one is 2 times bigger than this one, if A is 80, what is O1? O1 will be 2 times 80, which is 160 degrees. Thank you.